So this section is going to review your exponential growth, exponential curves in general, and you don't need to do them separately. We just want to point out to you guys that they can go two different ways. So, for example, it depends on the base. So if your base is greater than 1, that means the number being raised to the power of x is greater than 1, and I'll use 2 as an example, but basically both of these equations are set up as some base with x. The bummer is the base can be any number, so like with our quadratics and our square roots and cube roots, there was one parent function, exactly one. Here you have to build the parent function based on the base, okay? And a decay curve would have a base that's less than 1, so I'm just going to use 1/2 as an example here. So you'll want to make a note that this base is less than 1. So what does this look like? So we're going to go back with exponential functions to using -2, -1, 0, 1, and 2, but you have to think about what those powers are when they use this specific base your problem has given. So in this problem, I can use 2. So 2 to the second power, that would be 4. 2 to the first power, that'd be 2. 2 to the 0 power, a reminder again that anything raised to the 0 power is 1. And then 2 to the -1, a reminder of how these work. 2 to the -1 power is the reciprocal, or 1 over 2 to the first power. So you already have 2 to the first power on here, it's 2. So if you made that a -1 power, you'd get the reciprocal of that, 1/2. And same for -2, you already have 2 to the second power is 4. So 2 to the -2 power would be 1/4. So when you plot these points on here, I'm going to give us these points, and you'll notice you see this curve happening, and it's getting closer and closer to 0, but it will never actually reach 0. Remember, we discussed this when we were talking about logs. What power can you put on 2 to get 0? That's the same as asking, what's log base 2 of 0? That's not calculatable because there's no exponent that turns anything into 0. So it has here what we call an asymptote. A line marking a boundary that our graph gets closer and closer to without ever actually touching. It's a very interesting mathematical idea that because there are infinitely many numbers, you can keep getting smaller but never technically reach 0. So that's kind of what's happening here. The equation for these asymptotes in our parent function is always at 0. If we shift our graph up and down, we'll see that that will change. So what's the difference if we use a base of 1/2? You'll see the curve go a slightly different way. We will do the exact same thing to build the parent function, but remember now to calculate the y value, you're doing 1/2 to the power of 2, which is 1/4. 1/2 to the power of 1, which is 1/2. 1/2 to the power of 0 is 1. 1/2 to the power of -1, remember, is the reciprocal of what you got when you did 1/2 to the positive 1, so this will be 2. And then the same idea with -2, so this will be 4. And so look at the points that you see here. You see the same pattern but curving a different way. So the point just being, we're not going to treat these really differently. We're not going to do separate ones for decay and separate ones for growth. We just want to point out that though an exponential has a distinctive curve, you can build the parent functions the same way for each of them, and they have the same asymptotes. Just be aware that they could curve either way, okay? And that's how we build our parent functions. So these are your parent functions for these, but we can change the base of 2 or 1/2 to many different numbers. So we're going to do a couple of examples. So for the first function, notice that it's based on a parent function with 2. So for our table of points, the parent function would be based on a base of 2 as well. And you guys actually have this one above in your notes. So I'm just kind of getting those values from there. And don't forget your asymptote. So my asymptote is a y value of 0. And now I'm going to go through and do the transformation. So the only thing here that I see is this a value. And if you're a little confused about how these would be written with a's and b's and h and k, you have your base That's not a transformation. That's part of your parent function. Your b and your x minus h would now be in the exponent because that's where all of the x stuff is happening for this equation, and your a would still be in front and your k afterwards. So here there's only an a value of -3. So in our table, that means it will only affect the y values and the x values will stay the same. So all the y values are going to get multiplied by -3. So we will see these changes. Writing them down. And then even your asymptote, since it's a y value, you can perform the same transformations on it that you've performed on all the other y values. So it was 0. 0 multiplied by -3 is still 0. So I would still expect to have that asymptote at y equals 0. So I still expect this here, and it's nice for you to draw that in because it gives you some idea that all your points should be on one side of this asymptote and you should be able to create a curve. So let's see if that works for us. -2, -3/4, -1, -1.5, 0, -3, 1, -6, and then 2, -12 I don't have room for, but I can see the curve here. And I can see the curve get close to the asymptote, so that's what I want to be able to see. So our transformations, given that they were happening to a, are all vertical. A is being multiplied by a negative and a 3. So there is a vertical reflection because of the multiplication by the negative, or if you would rather say it, that's a reflection over the x-axis. And then there's also a vertical stretch because of the 3. Your h and your k values, we're actually not going to write them as points, but just make sure you can identify them. So our h was 0 and our k was 0. Do you guys see why we're not writing it as a point? For this function, it didn't start at 0, 0, so we don't want to confuse that with a point on our graph. The domain here is all reals. The function still covers all area left to right, and you can plug in anything you want, but the range is definitely limited. You can see that our whole graph is below that asymptote at 0, and it never hits the asymptote, so its y is less than 0, not equal to 0. Or in other words, from -infinity up until 0, but with a parenthesis, not a square bracket, because we do not equal 0. And then I'm going to go ahead and do the same thing for the second problem. And so this one, I do have some information up here with the B and the H. And so I do need to rewrite that just like we have been every time. So if I factor out -3, that will leave me with x minus 1. And all of that's in the exponent. Okay. The 1/2 is my base. So the parent function for this, or I'll write it in your chart, I apologize. The parent function for this is based off of 1/2 as the base. 1/2 is not a transformation. It is part of the parent function. And again, you have this one right up there. We've already created it, so I'm just using what I have from there. The transformations are these other values I see. So from my exponent here, I'm getting that I have a b and an h value. That b is -3 and h is 1. And then over here, I'm seeing that k is -1. So that means in my chart for x, remember we always use the reciprocal of b. So I'm going to multiply things by -1/3 and add 1 for the h. For my y values, I'm going to subtract 1. Okay. Oh, and then I'm not going to forget about that asymptote. It's nice to transform it with my table because then I get it right away. So I'm going to go through and multiply every x value by -1/3 and add 1. So -2 times -1/3 makes 2/3. And if I add 1 with that, I will just get 1 2/3. -1 times -1/3 is 1/3, and if I add 1 with that, I will get 1 1/3. With 0, I'll get 1. Negative or positive 1 times -1/3 will be -1/3, and I need to add 1 with that, and be careful here. I now have to think of 1 like 3/3, so I can clearly see that answer is actually 2/3. And 2 times negative 1/3 is negative 2/3, again added with 1, which I will think about like 3/3, which will give me 1/3. And now I'm going to go through and adjust all the y coordinates by shifting them down 1, so just subtracting 1. 1/2 minus 1 is negative 1/2, and 1/4 minus 1 is negative 3/4. And then I'm even going to adjust my asymptote. So 0 minus 1 is now at negative 1. So I'm going to fill in that asymptote, and hopefully I see all of my other points on one side of that and creating that curve that I expect for an exponential function. So 1 2/3, 3. 1 1/3, 1. 1 0. 2/3, negative 1/2. And 1/3, negative 3/4. All right, a little bit hard for me to get my points on here because they're kind of estimated, but I can see that curve, so I see it going upward. I see it curving around, and I know by its behavior it will start to get very close to that asymptote. Now to list my transformations. Look at what's happening to x. A 1/3 is multiplying it. There's a negative and a plus 1. That's 3 transformations. Because of the negative, there is a horizontal reflection. Or if you prefer not to say it that way, it's over the y-axis. Because of the 1/3, there is a horizontal compression. And because of the plus 1, there is a shift right 1. Then for the y value, having the minus 1, there is a shift down 1. Again, we're not going to write h and k as a point. It's important we can see the h and we can see the k because they're causing transformations, but they no longer make a point on our graph. Again, the domain is all reals. And the range for this graph, you can see your asymptote creating that boundary at negative 1, and the whole graph is above negative 1, never touching it. So greater than negative 1, or from negative 1 until infinity, but not equal to negative 1. And then the thing that we're missing on here are x and y-intercepts, so I do want to go through that. So for this first example, for the x-intercept, and I know you can see from the graph, but remember sometimes you're asked without a graph, so I want to make sure that you understand the algebra as well. So we would have 0 equals negative 3 times 2 to the x, and remember you want to get the exponent part alone, and then you want to use our exponential solving techniques. Can I set some things equal, or do I need to write it in log form? So we're going to divide by negative 3. So I have 0 equals 2 to the x. So there is no way to make 0 with exponents. So I can either recognize that right here, or I can try to write this in log form, which gets x alone and tells me my answer. But because I can't calculate the logarithm of 0, this is undefined. And so there are no x-intercepts for this equation. For the y-intercept, I'll be plugging 0 in for x. And so I'm going to go ahead and do that in our equation. So remember to follow your order of operations. So you want to calculate this exponential part first. Anything to the 0 power is 1. And negative 3 times 1 is negative 3. So our y-intercept will be at the point 0, negative 3. And again, you may have seen these from your graph, but sometimes you'll be asked without, and sometimes it's nice to do the algebra to check, because sometimes it will show you you did your graph incorrectly, and that would be important to know as well. Then we're going to do the same thing for the second example. So the x-intercept, we're going to plug 0 in for y. So we're going to have 0 equals 1/2 to the power of negative 3x plus 3, and then minus 1. Let me just make sure I copied that correctly. So first we want to get the exponential part alone, so I'm going to add 1 to each side. And then here is where we either want to write things with the same base or rewrite in log form. If I rewrote this in log form, it would be log base 1/2 of 1 equals negative 3x plus 3. And we can put this in a calculator or calculate it. The log of anything is 0, because remember, it's asking what power do you put 1/2 to get 1? And 0 is the exponent that makes things equal to 1. So that's 0. And then I would subtract 3 and divide by negative 3 to get 1. So my x-intercept is the 0.10. And again, you could see that in your chart, but some cases they won't be nice, neat values like that, so you need to know how to solve algebraically as well. For our y-intercept, we're going to plug 0 in for x. So I'll calculate that exponent first, and I would get 3. 1/2 to the third power will give me 1/8. And then in order to do this last arithmetic, I will think of 1 as 8 over 8 to have a common denominator. And that will give me negative 7 over 8. So my y-intercept is at 0, negative 7/8. And that makes sense with my graph. That's like almost at a -1. That seems to work. All right, we're going to do 2 more examples with different bases so you can see how you have to make a parent function if it's not 2 or 1/2. So notice this first function, okay? 4 is the base. So I want my parent function based off of 4. So I need to calculate 4 to these different powers. So 4 squared is 16. 4 to the first power is 4. 4 to the 0 power is 1. Remember that 4 to the -1 power will be the reciprocal of what you got with 4 to the first power. So it will be 1/4. And then -2 would give us 1/16. And then what are our transformations? So there's no b value here, but there is an h value of 2, and there is a k value of 1. So our transformations are going to be to shift to the right 2 by adding 2 to x. So I'm going to write that down. Shift right 2. And then to shift up 1 because we have that k value of 1. So shift up 1. And we also just found our h and our k. So I'm going to list those now too. So h is 2, k is 1. I'm also not going to forget my asymptote. I keep forgetting to write it originally, but it would be good if we have that here because we can just transform it in our chart. So I'm first going to take all the x values and add 2. And that's going to give me this new list of x values. I'm going to take the y values and add 1. So 1 plus a 16th is 1 and 1/16, like a little tiny bit more than 1. 1 plus 1/4 is 1 and 1/4. And you guys have a calculator, so you guys can get these in decimal form if needed. 2 plus 1 is 3. 4 plus 1, 16 plus 1. And even my asymptote, 0 plus 1, will now put the asymptote at 1. So remember my goal, that asymptote really helps give me a significant part of my graph. I understand where the graph should curve and kind of go towards, and then hopefully I see the points doing that. So 0, 1 and 1/16. So just like a tiny bit more than 1. 1, 1 and 1/4. Also very small, but a little bit bigger than the last one. 2, 3. 3, 5. And then I don't have enough room on my graph to graph 4/17, but I can see the exponential curve and I can see it getting close to that asymptote. Again, the domain is all real numbers. And the range here, we can see that it's y values above our asymptote of 1 or from 1 to infinity. And I'll come back and do, actually we can do them right now. So I'll do the x-intercepts for this. And again, I know if you have the graph, you can see, but what if you don't have the graph? So again, first you want to get the exponent alone. So I would subtract 1. And I can rewrite this in log form. That's log base 4 of -1 equals x minus 2. But you can't calculate the log of a negative. So this portion is uncalculatable or undefined, which means you can't finish the calculation, and that tells you there's no X-intercepts. For your Y-intercept, you're going to do 4 and plug in 0 for X. So that's 4 to the negative 2. Again, remember 4 to the negative 2 is 1 over 4 to the positive 2 power. That gives us 1/16. And that gives us 1 and 1/16. So our Y-intercept is the point 0, 1 and 1/16. Or you guys can write that in decimal format if that helps you since you have the calculator. All right, let's look at this last example. So notice that this one is based on having a base of 1/3. So I need to build my parent function, same x values, but now those are going to be powers, and same asymptote, but they will all be powers of 1/3. So 1/3 squared is 1/9. 1/3 to the first power is 1/3. 1/3 to the 0 power is 1. 1/3 to the negative 1 power will be the reciprocal of what I got of 1/3 to the first power, so it'll be 3. And 1/3 of the negative to the negative 2 power will be the reciprocal of the second power, which would be 9. So I am going to then make my transformation table. Look at our function. We have an a value of -2, an h value of -3, and a k value of 1. So x just has the adjustment by h, which is to move to the left 3, and y is going to get reflected and stretched by multiplying by -2 and shifted up 1 by adding 1. So I'm going to take each x value and walk through the subtraction of 3 here. So I get new x values, and then each y value I'm going to multiply by -2 and add 1. So for 9, that's -18 plus 1. For 3, that's -6 plus 1. For 1, that's -2 plus 1. For 1/3, it's -2 times 1/3 plus 1. So it's a -2/3 plus 1. I will think of the 1 as 3/3. So I can see the answer there. And then do the same thing with 1/9. -2 times 1/9 is -2/9 because we think about it as having a denominator of 1. I'm going to add that with 1, which is 9/9. That will give me 7/9. And then my asymptote, if I take that y value, multiply it by -2 and add 1, I just get 1. Okay, so my asymptote should be at 1. Hopefully we see points on one side of this and we can see how they curve. So -5, -17 isn't really going to fit on my graph. Let's try these other points. -4, -5. -3, -1. -2, 1/3. -1, 7/9. All I know is that 7/9 is pretty close to 1, or again, you guys have a calculator, so I can see this curve pretty well. See it curve back towards the asymptote. So my transformations, horizontally, I only had the -3, so there was a shift left 3. Vertically, I see it was multiplied by a negative, so there was a vertical reflection. Or again, if you would prefer to say reflection over the x-axis. I see it was multiplied by 2, so there's a vertical stretch. And I see that we added 1, so that's a shift up 1. Our h and k aren't really a point here, but we still need to see them properly. So h was -3 and k was 1. Again, our domain is all reals. And then our range you see is everything below 1, or from -infinity until 1. The X-intercept is going to be found by setting 0 equal to our expression here. And let me make sure I've copied it correctly. So we want to get this portion alone first. So I would subtract 1. and then divide by -2. So I had 1/2 equals 1/3 x to the x plus 3 power. And I would rewrite this in log form. So the base is 1/3. I'm taking the log of 1/2. The exponent is on the other side of the equation. Now, this is very complicated, but remember in our calculator, we can type that in as log of 1/2 divided by log of 1/3. And that will change the base. So I'm going to actually go use my calculator. And I'm going to do 1/2 and take the log of that. And then I'm going to divide that by 1/3 and the log of that. Oops. So I prefer the graphing calculator for this reason, but here I'll just find out what the log of 1/3 is, like a lot of you guys would do. So the log of 1/3 is negative 0.47712, and then I'll divide the log of 1/2 by that. So 1/2 the log of that, and then that needs to be divided by 0.47712, that's also negative, and that gives me 0.63. So this is 0.63, and then I'm going to subtract 3 from that, and that's going to give me a negative 2.37. So my x-intercept is negative 2.37 with 0. And then my y-intercept will set x equal to 0 and find y. So I will plug in 0 for x. That will give me 1/3 to the 3rd power. And 1/3 to the 3rd power is 1/27. When I multiply that by 2, that gives me negative 2/27. And again, I'm going to think of 1 as 27/27 to have that common denominator. And this will give me 25/27. And so then I have this y-intercept.